Our next presenter, it's another speech from CISCO guys. He's another CISCO fellow. He's a technical lead in CISCO, Ahmed Abdelsalam, and he will give us insights on IP measurement, IPM. Yeah. So thank you.
Thank you. Hello. Good afternoon. So many thanks for joining the session. And it's always a pleasure to be back at the MENOG event and present for the second year in a row. And thanks to the committee for giving us the opportunity. So today, discussion is going to be about IP measurement. My name is Ahmed Abdelsalam. I work as part of the segment routing team at CISCO. And we're going to cover the problem statement of the measurement in the IP network and the IPM solution to solve this problem. You have seen this slide previously in the session from my colleague Clarence, where he presented and explained how IP now is self-sufficient and being able to deliver any kind of service, being NFV, fast reroute, VPN, etc., across any domain, being access, metro, core, or in the data center, by removing all of the unnecessary shim layers. And with this, you gain all of the better reliability. And this is what SRv6 provides. And the second pillar of that solution is the IPM, or the IP measurement, which basically we designed the SRv6 solution to integrate the measurement from the first day. So the word IPM, you can look at this as IP measurement, but you can also look at this as integrated performance measurement that comes day one with deployment. And here, the way we do it is through active probing all of the time to measure all of the different ECMP passes continuously and correlating this with the routing data. So the focus of the session today is going to be on the IP measurement. Just to set the right context for the session of what we are talking about today. So the goal and the scope of that talk is basically the measurement part. And here we do the measurement from any edge to any edge in the network and across any ECMP pass. And how we do this? We basically do active probing from any edge in the network to any other edge, and covering all of the different ECMP passes. And in parallel and in addition to that, we continuously monitor the routing information to be able to build and detect all of the different ECMP passes that we have. And once we have these two pieces of information, we can use the analytics to correlate them to see if the measurements that you get are good enough compared to the current status of the network or not. And with this, let me explain what is the actual problem statement and how we're going to solve this and give you a hint on the intuition of the solution. Over the last years, operator has been investing heavily in network assurance, either in service provider where they deploy some probing appliance, external probing appliance that cost a fortune, or in data center network where they rely on host-based measurement, where they send many probes that treat the network as a black box, and as a result, you rely on solutions that is very expensive, cost a lot of operational costs, but at the end you get very low detection. And the reason that for that low detection is easy, because if there is one thing unique about the IP network is the ECMP capability. We use ECMP to increase, to have better reliability for load balancing, etc. But all of these probing solutions, they don't take ECMP into consideration. So in the legacy solutions that you have right now, what these solutions are missing? The first point is the scale. In order to measure all of the different ECMP passes at a good rate, you need to have a good scale of probing. The second problem is that when you measure what kind of information you export, or what are the different metrics that you export. Legacy solutions typically rely on minimum, maximum, and average, which basically hides the problem. It doesn't tell you much. And when you have a problem, typically you don't see it. One key problem also of legacy solution is the cost related to the solution, either CapEx or OpEx. And this is explained to you the common problem, which is that the operator cannot detect the problem before the customer. The customer detects the problem, they report the problem, and then the operator has to troubleshoot. And sometimes they have those issues going on for many days, and they keep experiencing this problem. So let's go a bit into the details of a bit of the nature of the IP network to understand the problems that we have. So we agreed that IP network rely heavily on ECMP. So this topology that you see here is a network topology of one of the operators that he presented in the Paris conference last year. And in some simple network, you can get up to 16 ECMP. But actually, that operator explained that the number of passes can go much, much higher. It can go up to 192 ECMP passes. The current probing solution, they completely ignore that ECMP nature for two reasons. Either because they don't have the scale to measure all of the different ECMP passes, or because they are poorly designed, or they don't take that ECMP nature in mind, and they send just probe packets, the same 5 tuple that will always take the same pass. So even if you have 16 ECMP passes and you send probe, you're going to measure only one of these passes. So what a measurement solution needs to provide? The first is to be able to discover, and it's important to discover and understand how many ECMP passes you have. The second is to monitor all of these passes. The second important requirement is to have enough probes per second to be able to measure all of the available passes. And the third is to report this information in an accurate way, not using minimum and maximum and average. And let me give you an analogy to understand a bit the problem when you don't have enough scale to do the measurement. The picture that you see here, it's the headquarters of a bank in London, and assume that you are the security officer of that bank. Would you accept that the camera coverage of your bank cover only 1% of the coverage space? Would you accept just having few cameras at the front door as a security officer? For sure, no. But let me ask you the question as a network operator. If you have a measurement solution that can give you visibility only into 1% of the passes that you have in the network, would you accept the solution? I think the answer is clear, no. So that's the problem that you have right now with the legacy solution. With the scale that they have, they can give you only 1% or even less or much less than what you need in order to measure the network. And again, that explained to you the problem that we discussed at the beginning, that the customer detects the problem, they report the problem to the operator, and the operator needs to troubleshoot. As an operator, you don't see it because you measure 1%, but your customers in total, they see all of the different passes that you have in the network. And how much probing scale you need in order to be able to measure a network. So let's start from how often you need to measurement. In a digital world, for AI application, for all of the gaming application, you need at least to measure once every millisecond. And take an example network of 500 nodes, typical size, or some networks are much, much bigger than this, and you have an average of 16 ECMP passes. You need 8 million probes per second at least to be able to measure this network. The shocking news is that the current legacy solution scale is typically 1,000 or even 10,000 less than what you really need in order to measure the network. And you end up having a coverage with only 0.1% or at best is 1% of the coverage. So the only solution to be able to have proper scale to measure your network is to be able to do the measurement and the probe generation and processing into hardware. And this is what we did in CISCO, in the CISCO Silicon One. We have the probing capability directly integrated in the hardware, so you can generate up to 14 million probes per second, but not only generation. You can also receive the probe, process them, and archive the data into hardware, so you simplify a lot also the SDN controller, and you don't, let's say, overwhelm your SDN controller with the amount of data that you need to send. And with this 14 million probe per second, what you need as 8 million probe is just only 57%, so you have way space to grow. The second point is the metrics. So now we solved the scale problem, and we can generate the probes directly from hardware at scale. The second problem is the metrics. How do you report the measurement? And let me give you an example based on the 16 ECMP passes that we just saw. So assume that you have 16 ECMP passes, and just one out of these 16 has a bad latency. What does it mean? It means that 6.25 of your clients are impacted by that bad latency. If you take all of these results and you take an average over the measurement of the 16 passes, the average is not going to tell you anything. It's going to see a bit of increase in the average, but you don't understand that if one or more ECMP passes are having issues. And what we do in the IP measurement is to provide what is called the latency histogram. And the latency histogram is a way to digitalize and see the distribution of the curve. So if your if your latency or expected latency is around 14 ECMP passes, so you're going to have a normal distribution of latency across this number 14. Some probes will take a little bit less, a little bit more, but you will see a normal distribution like the one that you see, the big one that you see in yellow. But if you have one pass that have an issue or have extra latency, you're going to see another distribution which is shifted from the normal one. So you can immediately understand that one of or more of these ECMP passes is experiencing a latency issues. So in terms of metrics, what do we provide? So the first thing is that previously what people were doing to measure the three main KPIs for network measurement, which is latency, loss, and liveness, is have separate session to measure every one of them. So the first thing is that with a single probe packet, we measure the three KPIs, latency, loss, and liveness. And the second, which is very, very key, is we do one-way measurement. And in order to explain this, let me give you a hint on how people used to do it. You send the packet, so I need to measure from Oman to Dubai. So you send the packets come back, you take the round trip time, and you divide it by 2. But now you are exposed to two main problems. The first one is that typically your upstream pass is different from the downstream. So you are dividing the latency by 2 while the pass is different. Even though your network or your pass is symmetric, so the same pass for an upstream and downstream are the same, you still cannot know if the problem or the issue that you have is in the upstream from Oman to Dubai or from Dubai to Oman. So it's really key to have this measurement one way. We can also provide per ECMP pass, which is, again, another key. You can start doing the measurement across the different ECMP passes, but you need to understand which ECMP pass you are measuring to understand which one has the issue. And this we can achieve thanks to SRv6 combined with the IP measurement, because we can strictly route the probe on a given ECMP pass and measure that pass. In terms of metrics, we provide latency histogram instead of min and max and average. We provide also the absolute loss, and based on the standard technique, which is alternate marking defined in RFC 9341, and we do liveness detection also in hardware. So you get the scale, you get the richer metrics, and by the integration on the hardware, you get this also at much cheaper cost, because by the integration in the hardware, we eliminate all of the CapEx related to the probing appliance, the router port that you need to connect your appliance to, also all of the OpEx cost, including the rack, the power, etc. And all of this IP measurement is based on standard simple TWAM packet format that is defined already in RFC, in these two RFC numbers that you see them. So it's a normal probe packet based on a standard format, and we encapsulate it with the SRv6 encapsulation. So that's the first part on the measurement. Once you have this accurate measurement, how are you going to know if the measurements are good or not? And this, the second point, or the second key contribution that we provide, is we provide a time series of measurement from anywhere to anywhere in the network across any ECMP path, but we also log all of the routing information to build a time series of the different ECMP paths. And now you get two time series, one with the measurement and one based on the routing information. And we can correlate the two to tell you if your measurement is good or bad based on the best topology. Also, if the measurement is good or bad based on the current topology, which can be a modified topology or a topology different from the one that you deployed. We can also leverage the routing analytics to do inference, so assume that you don't have full coverage of measurement in your network. And let me explain it with this example. You have measurement only from Paris to Madrid, but you have the London and Brussels. When they have to talk to Lisbon and Seville, they always go through that path from Paris to Madrid. If your measurement detect an issue between these two nodes and your routing analytics give you the information that London to Seville use the same path that has a measurement issue, so you can already infer the problem. So basically, to conclude, with SRv6 and IPM, the IP protocol now is self-sufficient and better than ever. You can deliver any kind of service using just native IPv6 encapsulation using SRv6, and you can measure any of these services using the IP measurement protocol to have, which give you the scale, the accuracy of the metric, and allow you to correlate the information with the routing to pinpoints where is the issue in your network. Thank you.